Hi everyone, today we're going to be talking about systems of linear equations and how to solve them. So the first question I guess we should ask for this topic would be, what is a linear equation? Well, as the name hints, an equation is any mathematical expression that contains an equal sign. And the word linear suggests that when we graph a linear equation, it's going to be graphed as a straight line. And the final characteristic of linear equations, at least the ones we're going to be dealing with, is that they have two variables, x and y, a and b, y and z, etc. So let's talk about these a little more in depth. So here we have three examples, 1x plus 4y equals 5, y equals 3a minus b, and 5y plus 1 minus x. So of these three, which would be considered equations? Well, we see the equal sign in the first two, and then no equal sign in 5y plus 1 minus x. So that is the only one that's not an equation. So a linear equation is an equation whose graph is a straight line. So of these three, which ones would be linear equations and which wouldn't? And you're probably way ahead of me. C is the only one that is not a straight line because it curves, and therefore it's not a linear equation. So finally, linear equations have two variables. Again, here are three examples. Take just a moment to look at them and see which ones you think would qualify as linear equations. Okay, we have x and y in the first example, x and y in the second, and a and b in the third. So all three of these, because they have two variables, their graphs would be a straight line, and they contain equal signs, are considered linear equations. So we aren't just talking about linear equations, we're talking about systems of linear equations. So what would a system of linear equations look like? Well, much like a solar system is a group of stars and planets, an ecosystem is a group of plants and animals, a system of linear equations would be a group of linear equations. So if you were taking a test and you saw a question that said something along the lines of, solve the following system of linear equations, and then it gave an example such as this one, y equals 4x plus 5, and 2x plus 3y equals 15. Or number 2, number 3, those are all systems of linear equations, okay? And one thing I want to note that is indicative of a system of linear equations is that the variables in the two equations that you're given, usually it will be two equations if you're solving for a system of them, are going to be the same. So for example, in one, we have x and y in the first equation, x and y in the second. We're not solving the first equation, x and y, and then the second equation looking for a and b. If you're solving a system of linear equations, you're usually going to be solving for the same two variables. Okay, and the same is true for numbers 2 and 3. So what do we mean when we say solving a system of linear equations? As we kind of already talked about, any linear equation can be graphed on an xy coordinate plane. And if it is a linear equation, then it will be a straight line. So one linear equation may look like this, and another linear equation may look like this when graphed. So as long as two lines are not parallel, somewhere on the coordinate plane, they are going to intersect. And that's what we mean when we say solve a system of linear equations. We want to find the point where the graphs of those equations would intercept. Okay? And those are written as an xy coordinate. So there you see the solution to a linear equation is expressed as an xy coordinate. So this is important. If you remember in a couple of the examples we've already shown, the variables in the equations themselves are actually a and b, not x and y. But once you graph that equation, well, you have to plot it on a coordinate plane, which has an x-axis and a y-axis. So when you're graphing an equation that has something like a and b, not your typical x, y, you would have to plot one of those variables on the x-axis, one of them on the y-axis. Therefore, the solution is still going to be a point on a coordinate plane, x, y. So to solve a system of linear equations, there are two different methods. And the first is graphing, which is kind of self-explanatory in that if we're looking for where the two graphs of systems of linear equations would intersect? Well, we're kind of hinting that we could just graph those and then find where they intersect, just like we did in the previous slide. So here we're instructed to solve the following system of linear equations: y equals 2x minus 2 and 2x plus y equals 8. So in order to graph these two equations, the first thing we're going to want to do is to make a t-chart for both of them. Okay, and when we make a t-chart, that's just xy coordinates, and we're inputting a given x or y and finding out what the other would come to if we solve the equation. Excuse me. So you could put in any numbers for these. We could see in the red equation on the left, we could see what y would be if we put in 1 for x, or what y would be if we put in 10 or 100. It doesn't matter. As long as you have 2 points for each line, you can graph the line. That's all you need to graph a line, are 2 points. However, the easiest way, usually, to find your 2 points is just going to be to find your intercepts. You want to figure out what y is when x equals 0, and you want to figure out what x is when y equals 0. And I think you'll see here in just a minute why it's easiest to look for the intercepts as opposed to just starting to plug in numbers. So if we're going to start with our red equation and start with x being 0, we would take our equation y equals 2x minus 2, plug in 0 for x, and solve. So 2 times 0 is 0, 0 minus 2, y is going to be negative 2. That's our first point. 0, negative 2 is our first point on the red line. So next we want to figure out what happens when, went a little bit ahead in the clicks, but you get the point. So when y is 0, we have 0 equals 2x minus 2, which then simplifies to 2 equals 2x because we would add 2 to both sides there. And then x is going to be 1. So for the blue equation, we're doing the same thing. If x is 0, we will have 2 times 0 plus y equals 8. And then 2 times 0 is 0, so y is going to be equal to 8. Same thing for y. 2x plus y equals 8, which would be 2x plus 0 equals 8. So we're solving for x. We divide both sides by 2, and x becomes 4. So those are going to be the 4 points that we'll use, 2 per line, to plot our line. So that's step 1. Step 2 is going to be to graph both lines and find the intersection, just like we've already talked about. So here are the t-charts that we created. Here's a coordinate plane. Let's go ahead and start graphing. First point for the red line is 0, negative 2. Remember, we go x, then y. So 0, negative 2 is going to be here. And then 1, 0, x, then y is going to be here. And we draw our line. Same thing for blue. 0, 8 is there. 4, 0 is there. And we draw our line. Once you have those two points for each line, it's fairly easy to go ahead and draw the line, and then you can estimate where they're going to intersect. Here, the intersection looks to be at about 2.53, and you may notice that one of the downsides of graphing to solve for systems of linear equations is that you can't tell exactly where the point is sometimes. You know, it looks like 2.5 to us on the x-axis, but it could be 2.6, 2.7. We can't really tell exactly, which is why we have the other method for solving them, okay? If you want to be more precise, you can use what's called substitution. So we're given a problem here, solve the following system of linear equations, and we're given 2 more equations. So you'll already notice this method does include one more step, takes just a little bit longer, but we can be more precise and we don't have to use any graphing paper or anything like that. So let's go ahead and start with step 1 in substitution. Step 1 says to isolate a variable. So we have our 2 equations here. We're working with the variables a and b. Now in either of those equations, it doesn't matter which one, we would just want to isolate a variable by itself on one side of the equal sign with everything else on the other side of the equal sign. You may have already noticed that conveniently, the first equation already has a b isolated. So technically, we could go ahead and skip this step because it's already done for us. Our original equation, which was b equals 3a minus 12, actually had a variable isolated. But what if it didn't? What if we were given two equations where there was no isolated variable and we had to move some things around to make that happen? Let's say we wanted to solve for a in the blue equation. Well, the first thing we need to get rid of is that 2b, so we would subtract it from both sides to get 4a equals 16 minus 2b. And then the only thing on the same side of the equation is the a is the 4, so we're going to divide everything by 4, which is going to give us a equals 4 minus 1/2 b, because 4a divided by 4 is a, 16 divided by 4 is 4, and then negative 2b divided by 4 is going to be minus 1/2 b. So there's our a isolated. Well, what if we wanted to get this b isolated? Kind of the same deal. We're going to subtract 4a from both sides, just to move the a to the other side of the equal sign. Then we're going to divide everything by 2 because there's a 2 next to the b. And when you do that, 2b over 2 is b, 16 divided by 2 is 8, and minus 4a divided by 2 is minus 2a. So then we have another b isolated. And just to show you could have done it with any of the variables, you can do the same thing here. Okay, and then you would get a equals b divided by 3 plus 4. So you can isolate any of these, but let's go with our OG here, the one we had from the very start, so we wouldn't have had to do this work at all. b equals 3a minus 12. And you'll notice I have these in parentheses already. I just went ahead and threw everything besides the b into parentheses because that's how we're going to use it in step 2. Okay, so here are our equations. We have the b isolated. Even if we hadn't started out that way, we could have done some moving around with the numbers. As long as you follow order of operations and correct procedures, you can move an equation around as much as you like, however you need, until you get a variable isolated on one side. And then you have b equals 3a minus 12. So that's our isolated variable. So the reason substitution works is that we have b set equal to something in terms of a. We have one variable which is equal to something in terms of the other variable. So in this other equation, we also have a b. We know that b equals 3a minus 12, so why don't we substitute that for the b in the other equation just to get us down to one variable? We'll take the b out of the equation. So now we get 4a plus 2 times what we know b is equal to, 3a minus 12, equals 16. And we're going to distribute that 2. So 2 times 3a is 6a. 2 times minus 12 is minus 24. And then the next step will be to combine like terms. We're going to add that 4a and the 6a to get 10a. So we have 10a minus 24. And then just add 24 to both sides. 10a equals 40. And divide by 10 to get a equals 4. Okay, so the reason you isolate the variable is so that you can plug it into the other equation when that variable comes up. So we have our two equations. We've already solved for a. We just need to know what b is. Okay, and the way to do that is to follow step 3. Plug the solved variable into either original equation and solve. Excuse me. So it's important to note here that you could plug 4 into the red equation or the blue equation, and you're going to come up with the same answer. And this is because, if you remember, we're finding where these two graphs would intersect. We're finding the point on a coordinate plane where the graphs would intersect. So it doesn't matter which of them you plug the 4 into, you're going to get the same answer. And I'll show you what I mean. Let's start with the first. If we plug 4 in for the a, we get b equals 3 times 4 minus 12. Well, 3 times 4 is 12, therefore b is 0. So we know that b is equal to 0 when we solve this system of linear equations. What if we had substituted the 4 in on the blue equation? Let's do it. We have 4a plus 2b equals 16, substituting in that 4 that we had when we came to this slide, and then 4 times 4 is 16. You get 16 plus 2b equals 16. Subtract 16 from both sides to get 2b equals 0, and then divide by 2. 0 divided by 2 is 0. So we're getting the same answer. If you remember earlier, we talked about how to write the solution to a system of linear equations, and that is as an x-y coordinate. So even though we're working with the variables a and b, when we plot this on a graph, we're going to need to throw one of them on the x-axis, one of them on the y-axis. Just to keep alphabetical order going, let's put a on the x-axis and b on the y-axis to get the point 4, 0. And that's how you would work with substitution. So the two methods of solving systems of linear equations are graphing and substitution. So here are a few practice problems that you can pause the video and try to work out on your own. So it says solve the following systems of linear equations using the given methods. We have graphing and substitution. So if you don't feel comfortable doing these on your own, I'm going to make another video where I do them and you can follow along with each step, and then hopefully that will help you out in solving systems of linear equations. Thank you.